Good afternoon, and today I will good afternoon. So today I will discuss about diagonalization and its application. So last week we stopped at algebraic multiplicity and geometric multiplicity. So let's discuss about little bit which things, and then we'll move to the application. So whatever I said about algebraic multiplicity and geometric multiplicity is that basically algebraic sorry. Uh, Algebraic multiplicity is basically the repetition of eigenvalues. So if A is a matrix, square matrix, definitely, and let's say it has an eigenvalue. A is a square matrix of, let's say, 3 cross 3. Okay, 3 cross 3 square matrix. So, and it has eigenvalues something like lambda 1 equals to lambda 2 equals to lambda. That means the two eigenvalues are same, and third one is lambda 3. So that means, so the algebraic multiplicity of lambda is basically 2, and algebraic multiplicity of lambda 3 is 1. So how many times the lambda repeated is basically the algebraic multiplicity. And uh, yeah, so and the geometric multiplicity is basically corresponding lambda. If we get uh, 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 we know that for individual lambda we get an eigenvector. So if a lambda is repeating, that means we should get two linearly independent eigenvector, right? But it is not the case for every time. Sometimes it happens that for a repetitive eigenvalues, we get only one eigenvector. So in that case, so the geometric multiplicity of that eigenvalues is basically 1. So so if we do the geometric multiplicity, so we can say that so number of independent number of independent eigenvector corresponding to eigenvalue, right? So that means in that case, if we consider this matrix, if we consider this A 3 cross 3 matrix, and it has three eigenvalues, out of which two is repetitive and one is distinct in nature. So in that case, if we consider this type of matrix, so if we get two independent eigenvectors corresponding to eigenvalue lambda from previous case, then the geometric multiplicity of lambda is 2. Otherwise, if we do not get the independent, if we do not get the independent eigenvalue, if we do not get the independent eigenvalues corresponding to lambda, if we get the one eigenvalue, that means the geometric multiplicity is 1. And we know that obviously this lambda 3 is distinct, so definitely we get, and its algebraic multiplicity is 1, so we get definitely an eigenvector which is definitely independent from the other two eigenvectors or other eigenvectors. So we will see an example like for repetitive eigenvalues when we get different independent eigenvectors, when we do not get the independent eigenvectors. So let's say an example. So consider matrix So this is matrix 0, -1, 0, 2, -3, 0, and 0, 0, 1. So this is the matrix. So we have to find out the eigenvalue. So basically, a minus lambda equals to 0, and we have to do is minus lambda -1, 0, 2, -3 minus lambda 0, and 0, 0, 1 minus lambda. So I'm not doing the complete, I'm not doing the determinant, sorry. So I have done it previously, so I just write it down the eigenvalue. So if we calculate this term, I calculate this equation, we will get lambda 1 equals to -2, and lambda 2 equals to lambda 3 equals to -1. That means we have three eigenvalues, out of which two is repetitive. So now we have to find out the eigenvectors. So since we have, so why is it necessary why is it necessary that the algebraic multiplicity should equal to geometric multiplicity? So if it is not happen, in that case, let's say in this matrix case, if it is not happen that obviously for lambda 1 we get one eigenvector, and let's say if for lambda 2 we do not get the two independent eigenvector. Let's say we get one independent eigenvector. So in that case, we it is not possible to diagonalize this matrix, right? Because as we have seen previous discussion, like when we talked about diagonalization, there was a equation like this, right? So this was the equation like S inverse AS. So where S is the matrix which columns are basically the eigenvectors of matrix A. So if the columns of the matrix A is not independent with each other, we do not get the inverse. So that definitely this equation will never be satisfied. That means we cannot diagonalize the matrix. So in that case, to get the inverse of S, we need an independent eigenvector. So let's check whether the algebraic multiplicity. So in that case, the algebraic multiplicity is
Sir,
1. Yes, yes.
eigenvalue is -2, -1, 1 ବାହାରୁଛି।
Uh, I don't think it should be 1, it should be -1, right? Uh, Let me check. Just a minute, let me check. Just to hold on, I just open the MATLAB, online MATLAB. Yeah. Sorry, yeah, you're right. It should be -1. Okay, I think like now this is okay. So yeah, I think now this is okay. So in that case, and the algebraic multiplicity of this eigenvalue is basically 2. So definitely we will get the geometric multiplicity of this eigenvalue is 1 definitely, because for a distinct eigenvalue we get a distinct eigenvector, and we need that geometric multiplicity of this eigenvalue should be 2. So let's check whether this will happen or not. Okay. So now just now using lambda 1 equals 2, so what we have to do is basically a minus lambda 1 I v1, that is equals to 0. So what is the thing? A minus lambda 1 I. So lambda 1 is minus 2. Put lambda 1 over here and we will get the thing. So it is 2 minus 1 0 2 ma sorry minus 1 0, and here 0 0 2 minus 1 0, yeah, 0 0 1. So v11, v12, and v13. So what is basically the equation that we get? So we get 2v11 minus v12 equals to 0, and v13 equals to 0. So definitely the eigenvector v1 is, so this is 0, and if we take v12 equals to 1, then this should be half, right? This should be 0.5. So this is one eigenvalue. Oh, sorry, one eigenvector. Okay, corresponding to minus 2. Okay, so this is one eigenvector. Now, or you can write it like, if we consider this is always 0, and if we consider v12 is 2, then v11 is 1. So both are basically same eigenvector. It's just scaled up and scaled down. Right? Now we need to use the eigenvalue, that is lambda 2 equals to lambda 3 equals to minus 1. Okay, and now we have to check that whether we will get. So I call this is a lambda only, and this is minus 1. So a minus lambda I, and this is v2, that is equals to 0. So definitely, so lambda is basically 1 minus 1 0. This is 2, and this is minus 2 0, and this is 0 0 0. So in that case, if you see, we get only one equation, that is v21 minus v22 equals to 0, right? Because the row 1 and row 2 are basically same row. I mean, they are basically same, just multiplied with 2. Row 2 is basically multiplied, 2 multiplied with row 1, right? So in that case, v23, we can choose v23 anything. Like I mean, either any constant value, I mean, any either 1 or 0, or minus 1, minus 2, whatever the value you can choose, right? So in that case, if you see, we can get two different eigenvector. How? So let's say if we choose v23 equals to 0, right? So v230. Now what should be the v121 and v22? Let's say we can consider this v211, v22 is 1, or we can choose 1 1 1, right? We can choose V23 as 1 as well, because ultimately V23 multiplied with 0 everywhere. In every case, V23 is multiplied with 0. So it it can't create any problem if we choose it 1 or 0, right? Or we can choose, let's say, this 2 0 and this is 1. This is also an eigenvector, right? And if you see, so that means all are basically linearly independent, right? So in that case, like at least we can say the geometric multiplicity of this, we can't consider 0 0 0 as an eigenvector, because that is basically the trivial case. So 0 0 0 is not an eigenvector. Okay, so that means we can consider this any. We can choose any of these three. Uh, out of three, we can choose any two. That means geometric multiplicity of this eigenvalues is 2. So that means this matrix can be diagonalizable. That means if we can create a S matrix where the column is V1 and this is V2, and I'm calling it V2 prime. So that means all three are linearly independent. So we can't, it's rather, I would suggest that we have to consider the linearly independent one, right? So it's better because these two are linearly independent with this one. We can see it. We have to check like all the V1, V2, and V3. Whichever we put over here, they all should be linearly independent. They can't be linearly dependent. Okay. So it's better. I think these two eigenvector you choose, and from this eigenvalue, and this is the eigenvector you choose, because here you can see the third element are 0. So here also the third element is 0. So it's better you don't. I mean, I think these two are linearly independent. So just you have to check like which out of these eigenvectors, which three are linearly independent. You have to consider any two from here, and you have to consider this, and you have to check that out of these four, which are the linearly independent. So those three linearly independent eigenvector we have to consider to create an S matrix, just to get an inverse of this S matrix, so that we can diagonalize this matrix A. Okay, so you can do it in your home, and next example you can do it in your home. Like it is similarly, you have a matrix something like 5 minus 1 0 minus 1 5 0 and 1 1 4. Let me check. It has, yeah. So it also has a repetitive eigenvalue, and you will definitely get for repetitive eigenvalue you will get a distinct eigenvector. Okay. Now move to the next example where we will show that how about if the eigenvalues is repetitive but we will not get the distinct eigenvector. So I have a matrix something like 2 1 minus 2 0 2 minus 1. Okay, and then 0 0 1. So if we do the determinant, check first So if we do these things, we will get, so it's basically 2 minus lambda 1 minus 2, 0 2 minus lambda minus 1, and 0 0 1 minus lambda. So you will basically get, this is two eigenvalues which are repetitive, and lambda 3 goes to 1. So now we have to find out the eigenvector. So 0 1 minus 2, 0 0 minus 1, and 0 0 minus 1. V11, V12, and V13. So in that case, we can choose V11 anything, right? It, yeah. So now if we sorry. So, so what are the two equations that we get is basically V12 minus 2V13 equals to 0 and minus V13 equals to 0. So that means we can see that we have to consider V13 is 0, because that is the last equation that suggests that V13 has to be 0. So if V13 is 0, then V12 has to be 0. So in that case, we can't choose V11 as a 0, because 0 0 0 is not an eigenvector. So we have to consider it 1. 1 or any constant, any non-zero constant value. So this is one eigenvector that we get by using the eigenvalue lambda. Okay. So now you can see over here that we are not getting the we are not getting the independent eigenvector corresponding to the repetitive eigenvalue, which is 2. That means the algebraic multiplicity of this eigenvalue is 2, but the geometric multiplicity of this eigenvalue is basically 1. So that means we cannot diagonalize this matrix. Okay. So that means this particular thing, we cannot produce S matrix according to our previous logic, right? Because we do not get this two eigenvector as a column of S matrix. Otherwise, the matrix is become singular. So obviously, I mean, I'm not doing the eigenvector corresponding to the one, because that is in any way that is since it's distinct eigenvalue, so we will get a definitely linearly independent eigenvector. Okay. So what should we do to diagonalize this matrix? Okay. So in that case, the concept of generalized eigenvectors comes into the picture. So what is generalized eigenvector? So, okay, so this is the process to find out the eigenvalue, right? Now we have to find out a second eigenvector corresponding to the eigenvalue, which is 2, because we need to make a geometric multiplicity of repetitive eigenvalue, this repetitive eigenvalue to 2, because its algebraic multiplicity is 2, right? So what should we do? So in that case, we consider a generalized eigenvector system A lambda I U1 is a generalized eigenvector. Consider equals to V1. Okay. So that means if we multiply both sides by A minus lambda I, so we will get this kind of thing, right? So that means, so either you choose A minus lambda I U1 equals to V1, or you can consider A minus lambda I square U1 equals to 0, whatever is easier for you. So I'm choosing this equation because this is basically easier. Otherwise, I have to multiply a matrix. So in that case, anything up to this point is difficult to understand, please stop me and ask question. Okay. So what was the matrix? Better directly that one. So this is my matrix, and here I have U11, U12, U13, and here I have V1. What is V1 that we get is 1, 0, 0. So that means we have a two equation over here, which is which says U11 minus 2U, sorry, it's U12 minus 2U13 equals to 1, and minus U13 equals to 0. So definitely U13 is always 0 over here, but here U11 is 1, right? And we can consider this is 1, and we can consider over here either U11 0 or U11 1, whatever the thing, whatever you want, you can consider. I'm considering U11 as a 0, right? Because this could be an eigenvector. Until and unless this is a 0, the length of this vector is 0, we can consider this as an eigenvector. So definitely we get now distinct eigenvector corresponding to the lambda 2. Okay. And let's say eigenvector corresponding lambda 3 which equals to 1, which is basically, let's say v3, let's say, I'm not calculating, you can calculate it by yourself. So v31, v32, and v33. Okay. So that means now we can consider and we can consider this matrix, S matrix. So this is 1 0 0 v1, this is 0 1 0, and this is v31, v32, and v33. So definitely v31, this eigenvector, definitely this eigenvector will be linearly independent with this other two, because this eigenvector corresponds to distinct eigenvalue. So now we can inverse. Now, since this is a non-singular matrix, right now, right? This is a non-singular matrix. So definitely now we can diagonalize. We can use this equation, S inverse A is. We can take the inverse of S and we can diagonalize. So why this diagonalization is basically so much important? Because it is basically easier to the matrix this lambda, the matrix big lambda, and this matrix A. So when we diagonalize a matrix, uh, and we get a resultant matrix, that resultant matrix and the original matrix both have the same property. Okay, they may not look like the same, but they have the same property. Like they have they share the uh, eigenvalues, they share the eigenvectors, which are basically the properties of a matrix. So that means we can say it may possible that is basically the shifted version or scaled one, but they share the same eigenvectors, same the eigenspace is basically the same for lambda and A. That's why diagonalization is very much required. So up to this point is okay for everyone, right? So now in that case, let's say if we have let me just use as a node box. So let's say a matrix A be a 3 cross 3 matrix. Okay, and it has repetitive eigenvalues like lambda 1 equals to lambda 2 equals to lambda 3 equals to lambda. That means all the three eigenvalues are repetitive. So, which means algebraic multiplicity of lambda is 3, and let's say geometric multiplicity is 1. In that case, what should we do? What should we do? So obviously we get a minus lambda I v1 equals to 0. We get one eigenvector, and we see that obviously we do not get the multiple independent eigenvector from this equation. So that means geometric multiplicity is 1. So in that case, what we do this, as you have seen. So this is the second eigenvector. Now we need the third eigenvector. So what should we do? A minus lambda I u2. U2 is the third, let's say, generalized eigenvector. Okay, and equals to u1. Okay, this is the third eigenvector. Now, if there is a, I mean, like 4 cross 4 matrix and all the four eigenvalues are repetitive and the geometric multiplicity is 1, so in that case, you have to A minus lambda I u3 equals to u2. So in that way, you have to find out the generalized eigenvector so that you can diagonalize the particular matrix. Okay. So now comes to the real matrix. So real matrices are very easy to work with. Why they are easy to work with? Because if you see the real matrix, real symmetric, definitely, not only real, the symmetric, real symmetric matrix. So real symmetric matrix, they are basically very easy to work with. Why they are very easy to work with? Because uh, the eigenvalues are real. So this is the symmetricity condition, and its eigenvalues are real, and eigenvectors are basically orthogonal. Okay, or rather say they are basically orthonormal. It's not orthogonal, they are orthogonal, and the length of each eigenvectors are 1. So they are basically yeah, orthonormal, right? So in previous week discussion, we have already seen how to make two or more than two eigenvectors. Sorry, how to make two or more than two independent vectors into an orthogonal or orthonormal one using a Gram-Schmidt method. Gram-Schmidt method. Okay, so now in that case, in real matrix, in real symmetric matrix, so when we diagonalize it, we do not need to do that much calculation, because we know that the S matrix that we basically in our in real matrix case, a real symmetry matrix case, we are not going to use that S symbol. We use a Q symbol, because Q basically define the orthonormal matrices or orthogonal matrices. We basically rather defined by Q. So in that case, this V1, V2, and V3, let's say dot Vn are orthonormal to each other. So since they are orthonormal to each other, so definitely they are independent. So this is the property of orthonormality or orthogonality. So if the two vectors are orthogonal to each other, if the two vectors are orthonormal to each other, that means they are perpendicular, and the length of each are basically the dot product of this two dot product of v1 dot v1 is basically 1, and the dot product of v1 dot v2 is basically 0. So this is basically the property of orthonormality. Uh, so if the vectors are orthonormal, they are independent. Since they are independent, so definitely we can get a inverse of this matrix. And what is the basically in case of orthonormal matrix, we do not need to basically find out the inverse, because we know that for orthonormal matrix, Q inverse equals to Q transpose, right? So we do not need to do that much of work, and definitely the MATLAB do not need to do that much of work to find out the inverse, because otherwise finding inverse, and if the size of the matrix is big, finding inverse is very cumbersome process for a MATLAB or for any software as well. And transpose is basically just exchange the row and column. So this is not that much a cumbersome process. So that means our calculations is become very easier. So that's why real matrices are very good metrics. A real symmetric matrix are very good metrics. So now, so we have already seen that the advantages of diagonalizability is basically in previous class, previous discussion, we have already seen that whoever joined this previous discussion, we have already seen that the uh, diagonalizability, one advantage of diagonalizability is basically compute the power, right? So if you, I'm just not doing it properly, but I'm just revising thing. I'm doing one example from here, and then we will move to the another application. So yeah, so we have seen that in previous class we have seen that, so this is the property of diagonalization, this is the equation of diagonalization. So definitely we can do this kind of format. So now if someone says that you have to find out a square, you have to find out the eigenvalues of a square, so this is something like diagonalize the a square is basically a lambda square, because eigenvalues are same, eigenvectors are same, so matrices a's are same, and the diagonalized matrix, the eigenvalues are basically on the diagonal, which are basically squared one. So that means a to the power k is basically a lambda to the power k a inverse. Now we have done one example regarding this. Like here, the question says that we have a Fibonacci series, something like that, and we have to find out the 100th element of that Fibonacci series, right? So these two are the equation, because Fibonacci series, like you are basically given the first these two number. Okay, so first 0 and 1 is given to you, and now you have to complete the Fibonacci sequence. So this is basically fk plus 2 is equal to fk plus 1 and fk, and fk plus 1 fk plus 1. So we find out this as the equation. So here we get the A matrix. Okay, now we have a U0, which is 1 and 0, F1 and F2, F1 and F0. So we have to find out U100. So we find out over here that the matrix eigenvalues of this matrix, and we find out the eigenvectors corresponding to this matrix. Okay, and we put it in that format. We put these eigenvector because they are definitely lambda 1 and lambda 2 are distinct, so these two eigenvector are linearly independent. So we have done this kind of thing, and we get a to the power 100 equals to this. We get this kind of format. Okay, so this is basically, and I did not do the whole computation. So after computing whole these things, you will get the F100 term. So computing the power, if you continue the sequence without using this linear algebra concept, if you continue this sequence, it would take too much time to find out the F100 term for this sequence. So similarly, there are some other problems where it is required to find out the compute the power of a matrix, so which is very much easier by using this diagonalization process. So this is one advantage over here. Now we do one example regarding this thing. So the example is we have given a matrix which is 0, 2, 2, 2, 0, 2, and 2, 2, 0. Okay. So you have to find out the eigenvalue, that means determinant of A minus lambda equals to 0. And here we get lambda 1 equals to lambda 2 equals to minus 2, and lambda 3 equals to 4. Okay. So this is the eigenvalue that I'm getting. Okay. Now you have to find out, you have to check that whether we will get, whether that means the algebraic multiplicity of this lambda is 2 and the algebraic multiplicity of this lambda is 1. So now we have to check, we have to find out, basically we need that geometric multiplicity of lambda should be 2. Okay. So in that case, so what we have to do, so using lambda equals to 2, so what we get, so we get a minus, so it's minus 2, 2, 2, 2, minus 2, oh sorry, plus 2, 2, and 2, 2, 2. So this is a minus lambda I v1 equals to 0. Now if you do the Gauss elimination method, so definitely this kind of picture that you will get, right? This kind of picture you will get. So now here you can see that obviously, so what is the equation? 2v11 plus 2v12 plus 2v13 equals to 0. So we can choose. So how do we find out the null space? So if you remember, to find out the null space, what we have said in the previous in some previous discussion, what we have said. So here basically this is basically the pivot element, right? This is pivot element, and we have a two free column. Like we can choose v1, a v2, and it's v12 and v13, anything depending on our choice, and based on that we have to find out v11, right? So what we choose, so we choose, let's say first we choose v12 equals to 1 and v13 equals to 0. So if v12 equals to 1 and v13 0, so what would be our v1? So this is 1, this is 0, and this should be minus 1, right? This should be minus 1 because 2v1, yes. And now the next choice is, I'm considering v1, sorry, v12 equals to 0 and v13 equals to 1. So in that case, v1 should be, this is 0, this is 1, this is minus 1. So that means for repeated eigenvalues, we get distinct, we get independent eigenvectors. So that means we do not need to find out the generalized eigenvectors and all this. And then now we have to find out using lambda 3 equals to 4. We have to find out a minus lambda 3 v3 and v1 prime. So what we get, minus 4, 2, 2, all are minus 4, and this is 2, right? So V31, V32, V33. So either you can do the Gauss elimination method, or you can do. So I'm just using the Gauss elimination. That is basically the easiest choice for me. So I'm just doing this 2 minus for 2, and this is 0. Uh, Sorry, I have to make this one is 0 as well. So this is 2, right? So the R2 prime is basically half R1 plus R2, and R3 prime is basically half R1 plus R3. Okay, so this is 0, this is 0, this is minus 3, and this is 1 plus 3, this is 3, this is minus 3, right? And then the last thing is R3 prime is basically R3 plus R2. So what we get, 4, 2, 2, 0 minus 3 minus 3, and 0, 0, 0. So that means we get two equations. So we have to choose V13. If we choose V13 to be, sorry, it's not V13, it's V33. So if we choose V33 to be 1, okay, so in that case, V32 equals to plus 1, right? V32 equals plus 1. Now, if V32 equals to V32 and V33 both are plus 1, from this equation is 31, 32, 33, right? So if we put in first equation, in this equation, if we put V32 and V33 both are 1, 1, then what would be the V31? V31 should be 1. So that means V3 eigenvector is basically 1, 1, 1, right? Mm. This is the X3 eigenvector, V3. So we have two eigenvector. Now we have to check that this eigen. So what are the eigenvectors that we got? So I call it V1 is basically that I got is minus 1, 1, 0, minus 1, 1, 0. V2 that I got minus 1, 0, 1, and V3 I got 1, 1, 1. So if you see that the length of the each vector is not 1, right? To make this orthonormal, we need that the vector should be, the length of each vector should be 1, right? So first of all, we have to check that the dot product of V1 transpose V2 is 0 or not. So let's see, V1 transpose V2 is minus 1, 1, 0, and this is 1, minus 1, 0, 1. So what we got, 1, 0 plus 0 plus 0. So that means we can see that here, so V1 are not perpendicular to V2, right? V1 not perpendicular to V2. So we make this is orthogonal, but they are independent. These two vectors are independent. You can see that these two vectors are independent, but they are not sorry, this should not be 0. This should be 1. This should be 1. So they are not orthogonal. Now check whether V1 and V3 are orthogonal or not. V1 transpose V3 is minus 1, 1, 0, 1, 1, 1. So what we got, minus 1 plus 1 plus 0. So they are orthogonal. Okay. And obviously, check V2 and V3 are orthogonal or not. So V1 orthogonal to V3, and here -1 0 1, and this is 1 1 1. So obviously we can see that this is 0. So V2 is orthogonal to V3. So now we have to make V1 and V2 to be orthogonal. Okay, so we remember the Gram-Schmidt process, as we have discussed in the previous section, previous discussion. We have section. So we have three linearly independent eigenvectors, and using Gram-Schmidt process we can make them orthogonal to each other, right? So I have a V2 and I need to make it orthogonal to V1, right? So it's a this is the I just copy this thing and paste it over here. So here the B vector is basically that is the vector we need to change. It is -1 0 1. Okay, and then capital sorry, and the capital A is the vector which is 1, that is the here the V1, which is -1 1 0 multiplied with -1 0 1 divided by -1 0 sorry, -1 1 0 multiplied with -1 1 0 into -1 1 0. So what is the structure? So this is basically nothing but 1 divided by this is 1 1 2 and -1 1 0. So what we get -1 minus half. Definitely this is minus half and this is 1. So now I need to change the notation over here. Let's say V2 prime equals to V2 V1 transpose V2 divided by V1 transpose V1 into V1. So now we have to check that V1, obviously V1 transpose V2 prime is basically right now is definitely it's a half minus half, and that is 0. That means these two are orthogonal. Now V2 prime transpose V3 are orthogonal, minus half, half, 0, and 1, 1, 1. So definitely they are orthogonal, as you can see. Okay? So all the vectors are now orthogonal. Okay, mutually they are orthogonal, but they are not still they are not orthonormal. Now we have to make them orthonormal. So for orthonormality, what we have to do? So let's say Q1 equals to V1 divided by norm of V1. Okay, so we have to divide all them by their norm. So what was, let me check. This is the formula, right? Yeah. So that means V1 divided by V1 transpose V1, right? So V1 transpose V1 root under, this is basically root. And what was the V1? V1 was -1 1 0, right? Now Q2 equals to V2 by norm of V2. The norm of V2 is basically 1 by 4 plus 1 by 4 2 by 4, 1 by 2, 1 by root 2 v2 prime, which is 1 by minus half 0, sorry, minus of half 1, okay, and q3 equals to v3 by norm of v3. v3 is 1 by root 3 is 1 1 1. So now your ultimately that matrix, which is minus 1 by root 2, 1 by root 2, 0, okay, and then minus 1 by 2 root 2, 1 by 2 root 2, and 1 by root 2, and then 1 by root 3, 1 by root 3, 1 by root 3. So this is basically the that eigenvector matrix. Now if you want to diagonalize it, you need q inverse a q. Now we do not need to do the q inverse because q inverse is equal to q transpose. So this is basically nothing but q transpose a q. Now if we do this thing, so you will definitely get some minus 2 if you do it by yourself, minus 2 minus 2 4. This should be the thing that you must get, because minus 2 are the eigenvector corresponding to the this eigenvector corresponding to this eigenvalue minus 2, this eigenvector corresponding to this eigenvalue minus 2, and this eigenvector is basically corresponding to this eigenvalue 4. So that means all the diagonal elements and all the off diagonal elements all are zeros. So that means you get the, it is basically the diagonalization process is basically easier if the matrix is orthonormal. Sorry. Now we do the next application of this whole diagonalization process. So now to find the quadratic curves, or what is the nature of this curve, this diagonalization process is very much effective to find. So to find the nature of the curve. Okay. So now we know that this is a quadratic curve, right? So this is basically a quadratic curve. Now, if you have given this kind of, so obviously here A, B, C, D, E, and F all are constant. So if you have given this curve to you, so it is sometimes it is difficult to find, difficult to say the whether that curve is ellipse or parabola or hyperbola or it's a circle. Circle may be easier because if the coefficient of x and y are a and c are 1 1, then it might become equation of a circle. Okay, but whether this whole thing is basically your the whole thing is basically whether it's a ellipse or parabola or hyperbola. So this is basically difficult to say from seeing the uh, quadratic curve by itself. Okay. So now for that case, I'm not doing the whole process. I'm just picking one example and do and see that how is things going, because the process already has been discussed in the lecture videos. Okay. So uh, so in that case, what we have to do, we have to basically we have to move transform we have to convert this equation into a canonical form, right? Canonical, what is canonical form? So what is canonical form? We have to convert this into canonical form. So what is canonical form? So canonical form is something like we have, let's say, a prime x square plus b prime y square plus some c not c a prime 0. So this kind of format, we have to convert it into this kind of format. So how we'll do this? We basically shifting the origin, and then we accumulate all the constant term into a certain format so that we get this kind of format. Okay. So I'm not doing the shifting origin type of scenario. Okay. So the equation question is, yeah. So you have given a quadratic curve which is 4x square minus 4xy plus 7y square plus 12x plus 6y equals to 9. So this is the quadratic curve that you have given. Now we have to see that whether this curve is an ellipse or it's a parabola or it's a hyperbola or what is this. Okay. Now if we shift the origin, so what we do, so basically let's say x tilde equals to basically x plus x naught, right? We have to shift the origin. Just a minute. Sorry. X equals to x tilde plus x naught and y equals to y tilde plus y naught. Okay. Now if you put all those things, x tilde plus x naught minus 4 x tilde plus x naught y tilde plus y naught plus 7 y tilde plus y naught square plus 12 x tilde plus x naught plus 6 y tilde plus y naught minus 9 equals to 0. So ultimately what you will get, you will get some sort of this type of equation like, sorry, this is 4 x tilde square minus 4 x tilde y tilde okay plus 7 y tilde square plus 2 uh, just a minute, I did something wrong over here. Did something wrong. What did I do? Something wrong over here. Just find out what is the wrong. Okay. Yeah, I understand. Okay. So now so here we will get something like 2 let's say d bar x tilde plus 2 e bar y tilde plus f bar equals to 0. Okay. So what is d bar? So d bar over here is something like 4x naught minus 2 y naught. Okay, because here if you compare this equation, if you compare this equation with this equation, so you will get that a here equals to 4, b here equals to minus 2, and c here equals to 7. Okay, and d here equals to, those are, I mean, obviously I can write it down. D here equals to 6, e here equals to 3, and f is 9 is given to you. So this is 4x naught minus 2 y naught plus 6, and we want to make this term to 0. So I equate this term to 0, and we have the another equation which is minus 2x naught plus 7 y naught plus 3. This equation is to 0, right? So that we get this kind of format. Why we need to this to 0? So that we get this kind of format: x tilde naught minus 4x tilde y tilde plus 7 y tilde square equals to minus f bar. We need this kind of equation because we can convert this, sorry, this should be square. Why we need this kind of equation? Because we can convert this equation into some sort of x transpose ax format. Okay, that's why we need this kind of equation, because these two linear term, basically we cannot put those linear term into some quadratic format, right? So for that, we can put this cross multiplication term into a quadratic format, into a matrix X transpose AX format, but we can't put this linear term into quadratic format. So we need these two should be zero. The D bar and E bar should be zero. And for that case, what should be the values of X naught and Y naught, so that this two should be zero, right? So from if you solve these two equation, if you solve this two equation, you will get that X naught equals to something minus 2 and Y naught equals to something minus 1. So here, if I need small here, right? So if bar here is basically nothing but a x naught square plus 2b x naught y naught plus c y naught square plus 2d x naught plus 2 e y naught plus small f. So these values, if you expand this whole thing, right? If you expand this whole thing and if you put all the x zeros term one side and all the x tilde term to the other side, you will get this kind of structure, because these things are constant, because we need to find out this x naught and y naught, that is the origin that we are basically trying to shift from 0, let's say from some 0 to somewhere else. So in that case, x tilde is basically the variable, x tilde, y tilde are the variable, and x naught, y naught are the constant term. So we put aside all the constant term one side, and we consider this as a f bar. Okay, so if you expand this, you will get this all the constant term as a f bar, all the term that is related with x only, this is called d bar, and all the terms which are related to y only or y tilde only, which is called as a E bar. And we need these two terms should be zero, so that we get a canonical form, that is ax square plus 2bxy plus cy square equals to some constant, right? So if you put the value of all the x naught, a, b, y naught, c, d, e, f, so you will get this is basically nothing but minus 24, right? So you will get something like minus 24. So definitely, so what was our equation? So that, so this equation can be written as 4x tilde square minus 4x tilde y tilde plus 7 y tilde square equals to 24, right? So how can we write this equation into a x transpose ax format? So, so we can write it in a x transpose ax format. So x transpose is basically x tilde y tilde this and this x tilde y tilde. So 4x square. So this term should be 4. 7y square. This term should be 7. And this is 4 in between. So mine. So we just need half, make this 1 by 2 and put it over here. And this is equals to 24. So this is now my A matrix, right? Because I mean, this is not the only approach you can do it. Maybe off diagonal elements are 4 and 7, but off diagonal elements something which is not minus 2 and minus 2. But why we choose minus 2 and minus 2? Because this makes this whole thing symmetrical, right? So we need to make this matrix to be symmetrical, so that our calculation become easier. Because for symmetric matrix we have seen that all the eigenvectors are eigenvalues are real and eigenvectors are orthonormal. At least they are orthogonal. Okay, so these are the two matrix. This is basically the matrix, and if we find out the eigenvalues, so this is 4 minus lambda minus 2 minus 2, 7 minus lambda. So this is lambda minus 8 and lambda minus 3. So we get lambda equals to 8 and 3, right? We get 2 lambda, and the corresponding eigenvector we have something like a minus, let's say, lambda 1 I v1. So we get minus 4. This lambda 1, this is 2, minus 4 minus 2 minus 2 minus 1. So this is basically, we can do 0, just multiplied, take a division of row 1 and subtract with row 2, we'll get this thing, right? v11 v12 equals to 0 0. So definitely if we choose v1 to 1, we choose v1 to 1, so this is, or rather if we choose v1 to 2, so this is 1. No, sorry, I did minus 4 v11 minus 2 v12 equals to 0. If this is 2, this should be minus 1, right? And then next is a minus lambda 2 I equals into v2 equals to 0. So what that be? 1 minus 2 minus 2, 4. v21 v22 is a similar, just opposite. So we get v21 minus 2 v22 equals to 0. So v2, so if 1 v22 I choose 1, then I have to make this thing 2. So these are the two eigenvector. Okay, so these are the two eigenvector and the quadratic. So if we diagonalize this, so now, so first of all, I have to check that v1 transpose v2 is orthogonal or not. Minus 2 2 2 1, so it become minus 2 plus 2, that is orthogonal, but they are not orthonormal, so I have to make this orthonormal. So let's say q1 equals to v1 by, okay, so root under 1 plus 4, so 1 by root 5 of minus 1 2, and q2 is v2 by, it's again 1 by root 5 2 1, right? So what is the matrix now? Is minus 1 by root 5, 2 by root 5, 2 by root 5, 1 by root 5. Okay. So now we have to diagonalize this matrix. So definitely if we do Q transpose AQ, we will get this matrix, right? So let's check. Minus 1 by root 5, 2 by root 5, 2 by root 5, 1 by root 5. This, what is matrix? What is the A matrix? It's a 4 minus 2 minus 2 7. So minus 4, this is 0, minus 4, no, so this is not 0, sorry. Minus 4 by root 5, minus 4 by root 5, it's minus 8 by root 5. And this one is 8 by root 5, and this is minus 2 by root 5, this is 6 by, sorry, ठीक है, 8 minus 2 is 6 by root 5, this is 2, so, and this is 2 by root 5 and 14 by root 5, so this is 16 by root 5, this is 4, 7, sorry, this is minus 4 and this is 7, so this is 5 by root 5. Just check the calculation whether I am doing anything wrong or not. 8 by 5,
So,
something. Yes, I did something wrong, I guess.
sir, see it is 16 by root 5 and 3 by root 5.
This one, this one. Are you
3
talking
by
about
root 5.
this one, right?
Yes,
Yeah,
sir.
yeah. Sorry. Yeah. Let me just do it in a calculator. MATLAB. Here. So this should be 3. This is 4 minus 4 minus 8. This is 8 by 5. This is 32. This should not be 32. This should be something 4, 8. 2, 14. Just a minute. Calculation, is there anything wrong? I couldn't find, but it should not be right. Just a minute. Okay. So Q transpose 4 minus 2 7. I think there is some minus 1, 2, 1. And here. Uh,
Sir,
yes, yes.
answer is 8003 baharuchi.
Uh, it's coming out as 8003.
Yes, sir.
And this one? this multiplication comes out as a 8003. I mean, ish,
Yes,
how?
sir.
Okay. So 8 plus 32 divided by 5. Okay. Yeah. 8003. Yeah. Okay. Sorry. My brain just got freeze for a certain time. Yeah. Thank you. So you got this diagonal matrix. So as you have seen that all the eigenvalues in the diagonal element, right? So now the thing is, now we consider, let's say, if we choose vector this x prime y prime as is q times x tilde y tilde. Okay. So what would happen? So in that case, we have this whole thing, right? We have this whole thing. So now we have this x tilde. I'm doing x prime y prime q transpose a q x prime y prime equals to 24, right? We can write it in that format. Now the q transpose aq, what is this? This is basically x transpose x prime y prime. This is basically lambda big lambda. This is thing, right? So that means we have 8003. So we have, that means 8 x prime square plus 3 y prime square equals to 24. So obviously, so this is basically the typical ellipse equation, right? This is basically the typical ellipse equation. So from here, it is, from this equation, it is difficult to understand whether the curve is a, whether this quadratic curve is a ellipse or hyperbola or parabola. So definitely this is not circle. This is for sure is not circle, because we have a coefficient over here is 4, and coefficient of x square is 4 and coefficient of y square is 7. So definitely this is not circle, but whether this is an ellipse or parabola is, or parabola or hyperbola. But if you plot it over here, but if you shift it and then do the shift the origin and then convert it into a diagonalized format, so definitely, so we understand that, okay, whatever the original equation, that equation was a ellipse. But if you plot it in a graph, so you can see that this equation, sorry, I just, where is the equation? Yeah. So this equation is basically let me just share my screen just for the time being, just to show you on a graph. So here I'm presenting. So the screen is visible to you, right? Screen is visible to you, right? Yeah.
No, sir.
You can't see the graph on the screen. I mean, in your because I
No,
have
sir.
shared.
I'm not able to see.
Okay, possible. If I can see my. Now you can see. Uh, uh,
No, sir.
Mozilla. None of you can see the screen of my laptop, like graph showing on a browser. Please confirm at least Deepranjan, Shobna. None of you can sharing my screen. Wow, how is it possible? My screen has been shared because on my deck. Okay, so Deep Deeptiranjan, Shobna, can you please confirm me? Will you able? Are you able to see my screen on not a web browser
Yes, sir. In the graph.
in the graph? Ravi Shukla, is it now? Is it visible to you?
I think, sir, I have in my laptop some problems is there actually. Maybe.
Okay, then there is a problem. Okay. So I mean, nothing much I'm discussing over here. I'm just showing that what is the original equation and what is the transform equation. Both are same, but they are basically rotated and shifted. This is what I'm saying. Both the equation are basically the same equation. They though both are both are your ellipse equation, but they are rotated and shifted. So the first equation was it was it was 4x² minus 4xy, sorry, square minus 4xy plus 7y square 12x plus 6y minus 9 equal to, just a minute, think the equation as plus 9, right? Oh, yes. Oh God, plus 12x minus 6y, right, plus 6y minus 9 equal to 0. So this is basically the original equation. Okay. Now, what equation that we received now, this is the another equation that we get after shifting the origin, minus 4xy plus 7y square equals to 24. Now the red one is basically the equation 2 that we get when we shift the origin from its actual position to the our required position x naught y naught, right? That is -2 -1. Now after diagonalizing, now after rotating, when we diagonalize it, we basically rotate the ellipse. So after rotating, what we get? We get 8 x square plus 3 y squared is equal to 24. Right? So we just that yellow one. So at first we get this one. So this is the original equation. Now after original equation, we shifted it over here from this position, from its original position to shifted position, right? And then we rotate it just to visualize, just to understand for our purpose. Okay, the diagonalization is makes us easier to understand that okay, this equation is now my ellipse equation. So if it is, let's say we get that eigen one of the eigenvalues is -3, let's say. So it is now become not an ellipse, it become hyperbola, right? So the scenario will different for that case. So this is basically that I want to show you over here. Nothing much. Move my screen over here. So this is basically the thing that we those are basically the application of diagonalization. And so first, diagonalization actually helps us to compute the power of matrix, and also it helps us to figure out the quadratic curves. Now, if as I have said that all the matrices, all the square matrices cannot be diagonalizable. Okay, if the matrix have a distinct eigenvalues, those for sure those matrices can be diagonalizable because distinct eigenvalues give distinct eigenvectors and those are linearly independent. Sometimes repetitive eigenvalues gives linearly independent eigenvector. That means for in case of repetitive eigenvalues, that algebraic multiplicity and geometric multiplicity, if they are equal, then we can say that the matrix can be diagonalizable. But if the case is that if there is no I mean, and the geometric multiplicity is less than the algebraic multiplicity, in that case it is not possible to diagonalize the original matrix. But for that case, we have seen that we make generalized eigenvector to get the S matrix non-singular, right? We formed a generalized eigenvector to get the next S matrix non-singular. Now, since this is the S matrix is now become a non-singular one, that means we can invert, we can find out the inverse of this matrix. But in that case, in this case, the diagonalization is not exact similar. So how it is, it's now become a Jordan block. So it is not has been discussed in the course, but just since I have discussed this generalized eigenvector, so I just make it complete over here. So in that case, I'm just doing it over here. Okay. So normally the diagonal matrix is something like lambda 1, lambda 2, lambda 3, and all are 0, right? All the diagonal, all the eigenvalues are in the diagonal and the off diagonal elements are 0. But if in case of repeated eigenvalues and they do not have the independent eigenvectors, okay, for that case we have to find out the generalized eigenvector. So in that case, our matrix, let's say M is now a diagonalized matrix, but this is something looks like this. Let's say lambda, I'm considering the 3 cross 3 matrix, and let's say it has two eigenvalues, which is repetitive and one is non-repetitive. I mean, one is definitely distinct. And we have geometric multiplicity of repetitive eigenvalues less than algebraic multiplicity. So in that case, so lambda, this is lambda 3. So these two are the repetitive eigenvalues. These two are the repetitive eigenvalues. So in that case, there should be that they create a block over here. So now it is not exactly diagonal. So this is something like, so this one is called Jordan block. This one is also a Jordan block. So that means for repetitive case, we can see that there is a not, they are not completely diagonal, but in off diagonal there is a one element is over there. One non-zero element is over there, which is wrong. So this block, these individual blocks is called, this individual blocks are called Jordan blocks. So in case of similar, so we are not say they are the diagonal matrix. They are basically similar to the diagonal matrix. So they are basically similar matrices. Okay. So this kind of it is not discussed in the course in that much detail. So I'm not going into that detail. But this is, since I have discussed this generalized eigenvector portion, so that's why I feel that I should discuss it. So this kind of picture you will get, right? So till now, do you have any problem, any query regarding all this? So you can ask. And obviously, my next weekend, I mean, that is the 15th March. The classes should be on 15th March, right? That is scheduled, but I have changed these classes on tomorrow. So tomorrow at the same timing, we have a class because I have some issues on that particular date. So 9th January, sorry, 9th of March, we have the last 8th of week class. So you can join over there. We will discuss the abstract vector space. So whatever the vector spaces that we have studied, we will study a little bit more in expand way. So we will discuss it tomorrow. And today's topic, regarding today's topic, do you have any queries? If you have any, please ask me. Or if you have not, then I can wrap this recording and this whole discussion.
Sir, in first page,
In first page, okay.
algebraic multiplicity and geometric multiplicity. That is.
Yeah. So algebraic multiplicity means when a matrix, where obviously when we find out the eigenvalues, if the eigenvalues are repetitive, the number of repetition is basically decide the algebraic multiplicity of that eigenvalue. So in that case, in this example, that I have considered that okay, A has a 3 cross 3 matrix and it has a 2 repetitive eigenvalues and 1 distinct eigenvalue. So obviously for these repetitive eigenvalues, the algebraic multiplicity is 2 because this eigenvalue is repeating twice, right? The repetition of this eigenvalue is twice. And for lambda 3, it is 1 because it appears only once. Okay, so this is the algebraic multiplicity. And geometric multiplicity is basically, we know that each eigenvalue we have a corresponding eigenvector. But for case of repetitive eigenvalues, do we have the same number of eigenvectors? If we have a same number of eigenvectors, that means if the number of repetition is n, then if we get n times eigenvectors, then we say the geometric multiplicity is equals to algebraic multiplicity. And then we can say, okay, that matrix can be diagonalizable. That we have discussed so far. So that means number of eigenvector corresponding to the eigenvalues, this defines the geometric multiplicity of an eigenvector. Sorry, geometric multiplicity of a particular eigenvalue. Is it clear? This is the question, like you want to understand that geometric multiplicity and algebraic, right?
Yes, sir. Sir,
Yeah.
in application of a spectral theorem of quadratic curves, that is
Uh,
used how it is used for in case মানে কো কেস রে এটাকে আমি ইউজ করি পারি
I mean, in which case we can use these kind of things, right? This is your
yes
question.
sir yes sir
So, in practical scenario, if you see, I do not find any kind of right now. I do not find the actual area to where we can use this. But in theoretical scenario, when we mathematically do something, sometimes we need to find out the curve. So basically, diagonalization is one of the help. I mean, this process is basically help us to find out the find out basically the nature of the curve and what type of curve it is, whether it's a ellipse, whether hyperbola, whether parabola. So nature of the to find out the nature of the curve, it is just like as I have said that from this equation, until and unless I plot this equation on a graph paper, it is by seeing this equation, it is difficult that this is a ellipse or hyperbola or parabola. You don't know, right? For sure, you can say that this is not a circle, but other than what type of curve it is, whether it's a something like uh, like normal polynomial curve, or is there something like elliptical curve or parabolic or hyperbolic. To understand the nature of the curve, this is basically the this diagonalization process basically helps us. So for that case, we first shift the origin so that we get the canonical form. And then by diagonalization, we just rotate that. This is basically the rotation. The diagonalization basically makes the rotation of the eigenvectors. Okay. So if you see, as if you see over here, if you see the eigenvector, so over here, if you so one thing is it's a -1 and 2. Okay, this is one eigenvector. Sorry, and another is 2 and 1. This is another eigenvector. Okay, so this is -1, 2, and 2, 1. So if we rotate this eigenvector, this is -1, 2, and this is 2, 1. Now about this origin, if you rotate this eigenvector, now you will see that it will take a shape of ellipse. Okay. Now here, just a minute. Last time I just sorry, 17. So if you see, this is basically our shifted one, right? Now if you draw the vectors over here, so if you draw the vectors, so you can see, so one vector is -1. Uh, just tell me what is -1 and then 2, right? So this is one vector and another vector is here 2 and then 1. If you see, so if you rotate this matrix, rotate this vector along about this origin, you can see this basically creates an. So what would be the AX? This is my vector X eigenvector. So what would be the AX? So for that case, the AX should be, in that case, this AX should be 16. So P equals to less than 16 comma 1, right? So W equals to vector comma. Oh, sorry. It's not 16 comma 1. It's t equals to, let's say, 16. So 8x1, 16 comma 8, right? So then W goes to vector A comma. So basically the major and minor axis are basically the, if you see, and if you write the P equals to 3, right? That is minus 3 comma 6, and I think J equals to vector A comma P. So if you see that the major and minor axis of the ellipse are basically nothing but it aligns with the eigenvectors, right? So it basically helps us to find out whether the matrix, whether the curve is basically elliptical curve or parabolic curve or something else. So it's nothing. I mean, theoretically, you can see this is. I hope you all can see my screen. So theoretically, if you see that there is, I do not. Sorry. Practically, if you see, I do not find. I mean, it's my knowledge is not that big, so that's why maybe I do not find the what actual application of this diagonalization. But theoretically, if you see, definitely this diagonalization process helps us to find out the nature of the curve, what type of curve it is. Maybe it is something when some calculation it is required to find out the nature of the curve. So the nature of the curve is required. So in that case, the process of diagonalization is basically necessary over here. Okay. So I think I'm able to help you this to answer the question. So is there anything? Uh,
No, sir.
so you can join tomorrow. We have a last week of class where we discuss about the abstract vector spaces. Okay. So thank you
Okay,
for
sir.
today.
Thank you.
Thank you for today. Okay.